right, so far there's only, well, there's really only one geometric or sequence that I've given you so far, and that's arithmetic. And that is, you have to add the same number every time to whatever you're getting. So like 1, 2, 3, 4, 5 is arithmetic, or 2, 4, 6, 8 arithmetic. We're adding the same common difference all the way through. A geometric is a little bit different. Geometric one would look like this. If I have 3, 6, 12, 24, like that. That would be what they call a geometric sequence. So take a second, just think about what the pattern might be for that. Or what we're doing. Maybe this is also geometric. If I go 5, and then 15, and then 45, and then 135. Okay? Both of those are geometric sequences. So that both of them are what? Multiplied by something. So instead of adding the same number all the way through the sequence, now we're going to multiply by the same number all the way through the sequence. So for this one, to get from 3 to 6, I multiply by 2. To get from 6 to 12, multiply by 2. 12 to 24, multiply by 2. So there's my pattern for that, is I'm essentially multiplying by 2 every time. On the bottom one here, I'm multiplying by 3 every time. For this geometric sequence, they call this a common ratio. Kind of like yesterday, we had a common difference. Basically, if I subtracted one term and the other term, that would give me my difference. Common ratio is if I divide those numbers. So if I take 15 and I divide it by the number in front of it, that ratio right there, a fractions ratio, that gives me 3. So that's my ratio right there. So your common ratio, or what we're going to call R is 3 for this particular one. For the top one, if I go 6 divided by 3, that's 2, so my common ratio here would be a 2. Okay, so we have common ratios for all of these guys. Thank you very much. Let me make sure of, whoa. Okay, got it. Thanks.
Would that be 15 over 5 instead of?
Yeah, I'm retarded. Got it. Thank you. Yeah, why did I put 5?
So it's R5?
I think I saw the 3 then.
No, so
Well,
because
15
it's
divided by 5.
Yeah, 15 divided by 5 is 3. Yeah, I just wrote. I saw the 3 there and wrote it. My bad. So now the nice part is for this common ratio, you can do it for any of the terms. If you went 135 and divided by the term in front of it, 45, that will still give you the same ratio. Okay, you still should get the same ratio all the way through. Okay. Now the common term for this, let's just develop kind of where this formula comes from. If I do this guy right here, a sub 1 equals 5, right? That's the first term for this guy right here. If I do a sub 2 for this guy, a sub 2 is 15, which is 5 multiplied by 3. If I do, slide that up, if I do a sub 3, it's really 5 multiplied by 3 multiplied by 3, right? I'm tacking an extra 3 on every time. If I do a sub 4, it's 5 multiplied by 3 by 3 by 3. Okay, now instead of writing those 3's out, all the time, notice that 3 is just going to get bigger and bigger and bigger. And I can write that in a different way. I can write that as 5 multiplied by 3 to the third power for this one, right? This one I can write as 5 multiplied by 3 to the second power, because there's 2 of them. This one I can write as 5 multiplied by 3 to the first power. A bit overkill. This one I can write as 5 multiplied by 3 to the 0 power. 3 to 0 is 1. 1 times 5, so I still get 5, right? So, a bit overkill, but if you do the fifth term, a sub 5, it's going to equal, over here, 5 multiplied by 3 to the fourth power. So notice the pattern there is that we're 1 less on our exponent right there. Okay, our exponent is 1 less than whatever term we want. Thank you. The general form for this, if I want the a sub n formula, for this one is going to be 5 multiplied by the ratio, which is 3, raised to a certain power. Now, the n is our counting number. I want to go 1 less than that for my ratio. So it's going to be the n minus 1. Okay, so 5 multiplied by 3 to the n minus 1. This right here is your geometric series. This is the equivalent of yesterday we did that dn plus c. We did the linear equation. This is the geometric version of it. Okay. Now, in general for a geometric series, geometric sequence, a sub n is going to equal the first term. That's 5 in this case, multiplied by whatever our common ratio is, so that's r, raised to the n minus 1 power. Okay, so that's kind of your generic for finding any nth term for whatever you're finding. Okay, that makes sense a little bit? Slide that up a little bit. Does that make sense? How we do that? Hopefully. Okay, so that's the general formula that we want to take a look at. So let's go ahead and write a term. Let's go ahead and find some stuff real quick. Let's say I give you the sequence. Let's go ahead and go 5, 10, 20, 40. So there's our sequence. And I want you to find a sub, let's keep it small. Let's keep it at 15. Okay, so let's find out how big a sub 15 is. first thing you probably want to do is write your a sub n formula, whatever our generic is, right? We don't want to keep doubling it all the way through and then, counting all the way to the 15th term. That would kind of suck. So I want to write my generic right here, a sub n. Now the first term we want a sub 1 multiplied by r to the n minus 1 power. So really I just need these two guys right here. I need the first term and I need the ratio, right? Assuming that it's geometric. So the first term is 5. So a sub n equals 5 multiplied by the ratio. Ratio was 2 on this one. So it's 2 raised to the n minus 1 power. Okay, we okay with that? Now if I want to find the 15th term, now I can just plug in 15 for n. So I'm going to have a times 15, a sub 15 equals 5 multiplied by 2 to the 15 minus 1. And just go ahead and put it on your calculator now and see what you get. So really it's 2 to the 14th, right? 2 to the 14th, put that on your calculator, multiply by 5. Let's skip over one. Ooh, I might have skipped over that one. Oh, that's fine. We're good. What did you get?
81,920.
81,920? Everybody else, hopefully a couple of you got that? Second that. All right, jackpot. Good. Okay, everybody's happy so far? So nothing real earth-shattering. It's still kind of like yesterday. We're going to base off of this formula right here and then plug stuff in. Okay. Let's make it a little harder. You guys ready to go a little harder? A little bit? Pre-calculus. We can go a little harder. I think. Okay, let's do, how hard do I want to go? Oh, let's do that one. Okay, how about find the 16th term, the third term is 5/4, and the sixth term will be 5/32. Now, today's notes should feel a lot like yesterday's notes. We're pretty much running through the exact same ideas as yesterday, just in the geometric series instead of an arithmetic series. Sequence. So, it might be a good idea just on the first one to go ahead and write out kind of what these guys are going to look like. It says the third term is 5/4. So, there's my third term. Then we got 4, and then 5, and then 6th term is 5/32. So on and so forth, Okay? So that's essentially our sequence right there. We want to figure out what the 16th term is, the 16th term all the way out on the end if we can. So on this one, to find a sub 16, I really need a sub n, right? I need some generic a sub n formula that I can plug a 16 into and then be happy. So for a sub n is once again it's the first term multiplied by the ratio raised to the n minus 1 power. So there's our generic formula for any geometric sequence. Problem is I don't have the first term and I don't have the ratio. I don't have either of those guys. So let's go ahead and solve for the ratio first. I think we're going to be able to do that first. If I want to go from 5/4 to this number right here, I'm multiplying by the ratio, right? So I'm essentially going multiply by r to get from here to here. Okay? To get from here to here, I multiply by another r. Right? To get from here to here, I multiply by another r. You okay with that? So I've multiplied by 3 r's to get up to this guy right here. Notice the 6th term, 3rd term, subtract, you get 3, right? So I have 3 of those r's right there that I'm multiplying by, which means I want to take 5/4 and I want to multiply that by r cubed on this guy. I'm multiplying it by 3 r's. Now don't put 3r because that's something a little different. That's r plus r plus r. That would be arithmetic. We don't want that. Okay? So it's r to the 3rd because I'm multiplying by 3 different r's right there. R to the 3rd really is r, right? There's 3 r's. And then that's going to equal this last term right here, 5/32. Okay? And we did something very similar to this yesterday. I believe we found the common difference, how many there were, and then set it equal to the number and divided, and everybody was happy. Okay? So to solve for r here, you first get rid of that 5/4. So multiply by 4/5. Multiply by its reciprocal. So these guys just go away. R to the 3rd equals, now let's see, these 5's cancel. 4/32 is 1/8. I think 4 is, yeah, that's right. Cool. Now we just take the cube root of that guy. So cube root both sides and we get our ratio, which is 1. Okay, so we have our ratio as 1/2. It's probably a good idea to double check that ratio just to make sure that we that we did it right. So if I go back up here on the sequence right here, let me put the ratios in there and see what we get. If I multiply 5/4 by 1/2, that's my ratio, I'm going to get 5/8. Ooh, that's kind of nice, that line's there. And then multiply 5/8 by 1/2, that's 5/16. Multiply 5/16 by 1/2, it's 5/32. Okay, so my sequence is looking pretty good right now. I like what I got. So now I can go into this formula and see what we get. So we have a sub n equals a sub 1 multiplied by the ratio, which is 1/2, all raised to the n minus 1 power. And we're pretty close. Now we need to figure out what the first term is. Now, a couple ways to do this. You could actually work backwards on that sequence right here. So if you multiply by 1/2 to get to here, you would divide by 1/2 to go the other direction. Well, dividing by a fraction, you multiply by its reciprocal. So essentially, I double that number right here to go backwards. So this would be 5/2, and this would be 5/1. And then my sequence would now make sense. So my first term there should be a 5. Now, let's say I gave you this term right here as the third term. Let's say that was the 30th term. You don't want to walk backwards all the way. That would take forever, right? So what I would do is I would say that this is a sub 3. A sub 3 is 5/4. That was kind of a starting thing they gave me. Well, let's plug that into the equation and then solve for a1 that way, just to make sure that it is 5, okay? So if I put an a sub 3 right here, that means I'm going to put a 3 in for the n spot. So I'm going to go a sub 1 multiplied by 1/2 to the n. N is 3, so I've got 3 minus 1 power. Little cleanup to solve for a sub 1. A sub 3 was 5/4. So 5/4 equals the first term multiplied by 1/2 to the second power. Right? 3 minus 1 is 2. So 1/2 squared, essentially, is 1/4. Now we're home free, right? Multiply by 4 on both sides. And so those cancel. You get your a sub 1 to equal 5. Now, like I said, that might have been overkill to do it on that one because, we could just work backwards on our sequence right here. However, if I gave you the 30th or something like that, if I was super evil, you might have to do a little bit of work there. Okay, so now we've got our a sub 1. So our general formula is this. It's a sub n equals a sub 1, which is 5, multiplied by the ratio to the n minus 1. So there's our generic. Now we've got to find the 16th term. Let's see what that looks like. Grossness. You'll notice a pattern, hopefully, on the sequence, right? It's 5 is all on the top. That 5 never changes. That's going to be kind of sweet. We're going to need that in a second. So let's say I want to do a sub 16. That'll equal 5 multiplied by 1/2 to the 16 minus 1. Essentially, just plug it into 16. Now, if you just put that on your calculator, right as it is right now, let's see what we get. We get something gross. I got did you guys get 1.52 times 10 to the negative 4th?
Yeah.
Okay, cool. So that's what that essentially equals. Now, if I look at my sequence, that doesn't really make sense, right? Notice my sequence is a nice pattern all the way through, right? So I want to have that not be a crazy decimal. I want that to be a nice, pretty fraction, like 5 over some number, right? You can see that's what that pattern's going to be. Well, okay, I'll hit math and then make that a fraction, and well, it doesn't do it for you, right? The scientific numbers, it doesn't like it too much on the fraction. So we have to cheat a little bit, okay? This is how we cheat for these ones. I will show you how we cheat. We know it's going to be a 5 on the top. That's what that 5 is going to be right there. Let's cheat on this 1/2 to the 16th. That's really, a sub 16 is 5 multiplied by 1/2 to the 15th power. I think everybody's okay with that. I hope. Sorry, guys. Okay, raise that to the 15th power. This is where it might get a little confusing.
Why is your name here? Yeah.
Anytime I'm going to be sarcastic, I'm going to raise my hand from now on. So 1 to the 15th over 2 to the 15th. I don't know. See, now it's over. I'm past the sarcasm. Okay, well, what's 1 to the 15th? So that 15th overkill, right? It's just 1. Right? 1 to the 15th is 1. Okay, that's good. Well, let's figure out what 2 to the 15th is. Put 2 to the 15th on your calculator. 32,768. So it's 5 multiplied by 1 over 32,768. So this equals 5 divided by 32,768. Now it's in our nice little sequence pattern, right? Double check it though. Go 5 divided by that last answer, right? I get 1.52 times 10 to the negative 4. It's the same decimal interpretation, right? So you can check your answer, which is kind of nice. But you got to maybe fake the funk in here just a little bit to make it pretty, make it a nice fraction. Okay? All right, we okay so far. We got to do summation still, but we okay through here. Essentially, the formula that you're going to want to have, I don't have written on this board. There, essentially, this is the big kicker for now. That guy right there. Okay, that's for geometric, and in geometric, you're going to use this guy right here. Okay? Now, the summation formulas are kind of gross. There's two of them. I'm going to give you one of them. Okay? You're welcome. I'll give you one. Because one of them is a little gross, a tiny bit.
That's why.
Okay, let's say I want to find what's called the partial sum for this. Now this one, it says find the first 7 terms of this series. Okay, so series, you just add all of them together. Okay, so this sequence, this is my sequence term right here. I want to plug in a 1, a 2, a 3, a 4, 5, 6, 7, all of those numbers, and add all of those numbers together. Okay. Now before, we had a summation formula for what we called the sum of the n terms from before. It was a sub 1 plus a sub n over 2 times n. That was the formula we used before. And that was for only arithmetic, though. Geometric has its own. Geometrics look like this. A sub 1, 1 minus r to the n power. So you're taking the first term, you're multiplying it by 1 minus the ratio raised to whatever n power that you have. Oh, and then divide that by 1 minus the ratio. Now, this formula right here is what they call a partial sum formula. So this is for a partial sum. Okay, so this is the formula for a partial sum. Now, we'll get there in a second for ones that are not partial, which means entire, whole, a lot. We'll take a look at that. Those are a little different. Okay, so let's go ahead and plug in, and I'm going to give you this formula. This formula don't memorize. Okay, I'm going to give you this one. So we're going to plug in our numbers for this guy right here. So we need to find the first term, a sub 1, right? So I'm going to find the sum of the first 7 terms. I want to find the first term, a sub 1, which is 3. A sub 1 is the first term. So you have to plug in the 1 right there. If you plug in a 1, 1 minus 1 is 0. 2 to the 0 is 1. 3 times 1 is 3. So the first term should be 3. Plus, if you notice, it kind of fits our little a sub 1 r to the n minus 1 pattern. And so that's the first term. Most of the time that works. The only time it doesn't work is maybe that's a 0 right there. Sometimes they start at 0 because they're evil. And sometimes that might not be a minus 1. Just might be an n. So you got to watch out a little bit. But a lot of times that number right there is your first term. A lot of times. Okay, then we go 1 minus the ratio. The ratio is the number being raised to the power. That's this 2 right here. So we're going to have 2 raised to the n power. Now, n, I'm doing the sum of the first 7 terms, so n is 7. So I'm going to raise this to the 7th power. Are you okay? Okay, cool. And then 1 minus r, which is my ratio, which is a 2. Just put it on your calculator. It's not too bad. I don't mind if you put it on your calculator. It'd be kind of hard to not do it on your calculator, right? 3 and then 1 minus 2 to the 7th. 128? Can they do that? 2 to the 7th, 128? Yeah. And 3 and then 1. Is it really? I screwed up. 381? Yeah.
I got 380.
125.
127 times 3.
Oh, okay, I know what I did. Got it. I was like, why did my brain not do that right? Yeah, I'm good. I did too. Oh, I did. Okay, so we get 3 to 1. That means that the first 7 terms of that sequence, if I add all those numbers together, that'll give me 381. Okay? Are we okay with that? That's pretty good. Now, what happens if I didn't want the partial sum? What happens if I wanted what they call the infinite sum? If I were to take this guy right here, instead of stopping at 7 now, I would go to infinity. Now, the problem is, if I keep adding numbers that are bigger and bigger and bigger and bigger, I'm always adding a bigger number, right? What's this going to eventually go to if I continue to add those bigger? Infinity. It's still going to just be grow without bounds. It's going to be huge, monster number, okay? However, if I make this ratio a little bit smaller, my geometric series can actually go to infinity. Let's take a look at one of those. So you see what I'm talking about. Let's go n goes from 1 to infinity. And let's do, which one do we want to do? Let's do that one. Let's go 2 multiplied by 0.1 to the n power. Now this one, notice what your r is. I'm just going to write on the side here. Your r is 0.1. Okay, that's your ratio, multiplying by 0.1 every time. If I were to write out the numbers for this, the sequence for this, if I could, what happens if I plug in a 1? What do you get if you plug in a 1? 0.2. The first term should equal 0.2. Plus, we're going to add the next term to it. That would be plugging in a 2. Well, 0.1 squared is 0.01 multiplied by 2, 0.02. Plus the next term. Plus the next term. Plus the next term, right? So what is this going to eventually get to? 0.2 repeating, right? It's going to go to 0.2 repeating, hopefully. I don't know if anybody knows what 0.2 repeating is. Anyways, let's figure it out. The sum of the infinite terms now. There's a second formula for this, but it's essentially the same formula as before, which is a sub 1 multiplied by 1 minus r to the n over 1 minus r. It's that same exact formula. However, our ratio for this guy, if I were to plug in infinity, our ratio and our a sub 1 part right here, let's see what that looks like. The sum of the infinite terms is going to equal the first term, which is 0.2. Notice that the first term is not just a regular 2 on this one, right? So you can't always just look at that front number. A lot of times it works out nice, but you can't always do it on that one. First term in that sequence was 0.2. So 0.2 multiplied by 1 minus 0.1, raised to the infinity power, divided by 1 minus 0.1. Now, this part itself is kind of weird, this 0.1 to the infinity power, right? If I take a number that's less than 1, that's going to be the key for this, and I raise it to the infinity power, what happens if you take 0.1, you raise it to the 1,000th power? What's this going to go to? Anybody know? It's going to go to 0. It's going to get smaller and smaller and smaller. This is eventually going to go to 0. Okay, well, then it's 1 minus 0, which is 1. So we effectively have 0.2 divided by 1 minus 0.1. So for the infinite series, this guy right here, so move that up again a little bit. The infinite series, that guy is gone. You don't need that part. That part just disappears. So the infinite series simplifies a sub 1 over 1 minus the ratio. Okay, now this 0.2 over 1 minus 0.1, let's see what this equals. Well, it's 0.2 over 1 minus point is that's 0.9. 0.2 over 0.9 is 2 over 9. Right? So it's 2 ninths. Now, if you put 2 ninths on your calculator, what decimal does that give you? Hey, 0.2 repeating, right? Jackpot. Gold. Okay? So if we have a sum, there's 2 different kinds of sums that you'll do with geometric sequences, okay? 2 different kinds of sums. The first one is what they call a partial sum, or a finite sum, a small number, okay, a fixed number. The other is what they call an infinite sum. So it continues on forever, and it keeps going. The only catch is, for this infinite sum right here, is your ratio has to be less than 1. Ratio's got to be less than 1. That's key right there. If your ratio is bigger than 1, then it's just going to grow without bounds. It's going to go to infinity. You'll never get an answer. Okay? So that ratio definitely has to be less than 1. A technicality, your ratio can be negative, so we might have to throw an absolute value on that r right there. So it's got to pretty much be between negative 1 and 1 if you were to confine it in a little domain there. Okay? Essentially, as you look at this guy right here, that number better be less than 1. If that number is not less than 1, you can't do an infinite sum.
So pretty much you're saying the partial sum is only for 1 3.
No, you can do a partial sum for 0.1. If I did, like, let's say I found the first 4 terms of this, that would be 0.2222. That would be a partial sum, right? And that would be, if you were to do that, that's 1, like 10, 100,000, 10,000. So this would be 2222 over 10,000.
Yeah.
Isn't that what that is? And then reduced? I'm pretty sure that's what that is. So that's a partial sum of it. The infinite sum would be 2 ninths. Would be the exact value of it, essentially, as it goes forever, as it continues. So, all right, cool. So that's pretty much it. The only hanger there is it's got to be less than 1. It's the only real weird part about the whole thing. So we're on 582. I need a little more time to finish up those tests. And we'll get it back to you.
just apples to apples.